There's a type of star that once existed that didn't burn anything, It didn't burn hydrogen, helium. It burned matter we can't see, can't touch, can barely prove exists. They're called dark stars, and they were monsters. A single dark star could be 10 million times more massive than our Sunday. If our sun were a ping-pong ball, a dark star would be bigger than a house. You could fit our entire solar system inside one with room to spare. They shone brighter than entire galaxies. Each one, a single star, outshining billions of normal suns combined. But we just discovered them. December 2022. By accident, let me tell you how. December 2022. Scientists around the world are staring at images from the James Webb Space Telescope. JWST had launched a year earlier, the most powerful telescope ever built, designed to see farther back in time than any instrument in history. Its mission was to photograph the baby universe, to see the first galaxies forming in the darkness after the Big Bang. And it worked. The images were stunning, sharp beyond anything they'd hoped for. Looking back over 13 billion years, seeing the universe when it was only 300 million years old. But there was a problem. Scattered across these images were bright red dots, faint, distant, ancient. At first, everyone assumed they were galaxies, baby galaxies, the first structures forming in the young universe. That's what they were supposed to be. Then someone measured their brightness and their distance and ran the calculations. The numbers didn't work. These objects were too bright, way too bright, and too massive. The amount of matter needed to produce that much light was staggering. These weren't small baby galaxies tentatively forming. These were massive, mature structures. But the universe at that point was only 300 million years old. That's like being 3 weeks old if the universe's current age were a human lifespan of 80 years. There simply hadn't been enough time to build galaxies this large. Think about what it takes to create a galaxy. You need billions of years. Matter slowly clumps together under gravity. Stars form, live their lives, die. New generations are born from their ashes. Gradually, over cosmic ages, you build up a galaxy with hundreds of billions of stars. Our Milky Way took over 10 billion years to reach its current size. Most large galaxies did. That's the normal timescale. But these objects JWST was seeing, they appeared fully formed when the universe was barely 300 million years old. It's like finding a full-grown oak tree in soil that was planted yesterday. Like finding ancient cities with towers and bridges that carbon date to before humans invented agriculture. The evidence was right there in the data. But the timeline made it impossible. Scientists started calling them universe breakers. The name stuck, because that's what they seemed to be doing. Breaking the universe, breaking the rules, breaking every model of cosmic evolution that had been carefully built up over decades. Papers started appearing with unusual titles. Panic. At the Discs one was called. Scientists don't usually use exclamation points in paper titles. That tells you how serious this was. Conferences were organized. Emergency meetings. Research groups around the world were running simulations, checking instruments, recalculating everything from scratch. The data kept saying the same thing. These objects exist. They're too big. They're too early. Something is fundamentally wrong. Two possibilities emerged. Either our entire cosmological framework was broken, the Big Bang theory, the lambda CDM model that describes how the universe formed and evolved. All of it might need to be thrown out and rebuilt. Everything we thought we understood about gravity, about how matter clumps together, about how structure forms in the universe, could be wrong, or we were misidentifying what we were looking at. These bright red dots weren't what we thought they were. For months, scientists leaned toward the first option, the scary option. Maybe the universe really was broken. Maybe JWST had discovered a fundamental flaw in our understanding of reality. The tension was incredible. Careers built on cosmological models suddenly looked shaky. Textbooks might need rewriting. Decades of work potentially invalidated. Then someone remembered something. An old paper from 2007, a wild hypothesis that most people had forgotten about. A physicist named Catherine Fries and her collaborators had proposed something strange back then. What if the very first stars in the universe weren't powered by fusion at all? What if they were powered by dark matter? At the time, it was an interesting theoretical curiosity. There was no way to test it. These hypothetical dark stars would have existed only in the first few 100 million years after the Big Bang, then gone extinct forever. By the time we could observe the universe, they'd been gone for over 13 billion years. The hypothesis was published, discussed briefly at a few conferences, then mostly forgotten. Filed away as one of those neat ideas that we'll probably never be able to confirm. Until now, someone on one of those panicked research teams remembered dark stars, and they started running calculations. What if those bright red dots weren't galaxies at all? What if each one was a single dark star? The math started working. A single, massive dark star, powered by dark matter annihilation instead of fusion. Existing in the early universe, when dark matter was still concentrated and dense, could shine as bright as an entire galaxy. It could produce the same amount of light as hundreds of millions of normal stars, all from one giant object. And here's the beautiful part. You can build a dark star in 300 million years. That's actually plenty of time. Dark stars don't need billions of years to form like galaxies do. They form more like stars, just much larger. A few 100,000 years for initial collapse, then growth over millions of years. 300 million years? More than enough. The timeline fits. For the first time since the crisis began, something fits. The brightness fits too. One dark star could be as luminous as a small galaxy. The color fits. The size fits. Even the spectrum of light matches theoretical predictions. Everything clicks into place. What everyone thought was a city of stars, a whole galaxy containing billions of individual suns, was actually one colossal giant shining alone in the darkness. The universe breaker crisis? Solved. Physics wasn't broken, after all. We were just looking at the evidence wrong, like detectives chasing what seemed like an impossible crime, then realizing they'd misidentified the culprit. One hypothesis that makes all the impossible data make sense. But here's the thing. The solution is so much weirder than the crisis ever was. We almost discovered the universe was broken. Instead, we discovered it had a childhood stranger than our wildest theories predicted. A childhood where stars could burn darkness, where giants 10 million times the mass of the sun could exist, where the fundamental rules of stellar physics worked completely differently than they do today. And that childhood can never come back. Because dark stars can only exist under conditions that no longer exist in our universe. Conditions that disappeared 13 billion years ago and will never return. So, how does a star burn darkness? What does that even mean? To understand that, we need to go back. Back to when the universe was young enough that impossible things were possible. Close your eyes and travel back with me. 13.5 billion years into the past, the Big Bang happened 300 million years ago. The universe is an infant. What does it look like? You expect darkness, maybe, tiny stars struggling to ignite, vast empty spaces, the beginning of structure, slow and tentative. But that's not what you see. You see massive glowing spheres scattered through space, each one illuminating enormous regions around it, shining fierce and bright. These aren't the tiny baby stars you expected. These are giants. And there's something else. Something you can't see, but can somehow sense. The universe feels different here, denser, heavier. That's because it does. The early universe was packed with matter in a way that's hard to imagine from our perspective. Everything was closer together. The universe was smaller. All the matter that today is spread across billions of light years was compressed into a much tighter space. And most of that matter, you can't see it. Dark matter, let me tell you about dark matter, because it's the key to everything. It's the reason dark stars could exist. It's the fuel they burned. Dark matter makes up about 85% of all matter in the universe. For every atom of normal matter, hydrogen and carbon and iron and all the stuff you're made of, there's about 5 times as much dark matter. It outnumbers us 5 to 1. The universe is mostly made of stuff we can't see. We discovered dark matter, or rather inferred it, back in the 1930s. Astronomer Fritz Zwicky was studying galaxy clusters, watching how galaxies moved within these massive groups. He measured their speeds and calculated how much mass would be needed to keep them bound together by gravity. The numbers didn't match. Galaxies were moving too fast. The visible matter, all the stars and gas he could see, didn't have enough gravity to hold the cluster together. The galaxies should be flying apart, escaping into space, but they weren't. Something invisible was providing extra gravity. Since then, we've found dark matter's fingerprints everywhere. In how galaxies rotate, the outer edges of spiral galaxies spin too fast for the visible matter alone. In how light bends around massive clusters, gravity from dark matter warps space, bending light from distant galaxies behind them. In the cosmic microwave background, the afterglow of the Big Bang, the patterns in that ancient light reveal how dark matter was distributed in the early universe. We can map where dark matter is by watching how it affects things we can see. We just can't see the dark matter itself. What is it made of? We don't know for certain. The leading theory is that it's a type of particle that doesn't interact with light or electromagnetic forces. Particles that only feel gravity and possibly the weak nuclear force. They can pass right through normal matter like ghosts passing through walls. These particles, whatever they are everywhere. Right now, billions of dark matter particles are streaming through your body every second. You don't feel them. They don't leave a trace. They just drift through, pulled by gravity but interacting with nothing else, except with each other. When two dark matter particles collide, under the right circumstances, they can annihilate, destroy each other completely. Their mass converts into energy, gamma rays burst out, heat releases. In today's universe, this happens extremely rarely. Dark matter is spread thin by 13.8 billion years of cosmic expansion. The universe has been growing larger since the Big Bang, and as it grows, everything in it gets more diluted. Dark matter particles can drift through space for billions of years without ever encountering another dark matter particle. The collision rate is essentially zero, but in the early universe? Different story entirely. 300 million years after the Big Bang, dark matter was thick, concentrated, packed together in a way that can't happen anymore. Particles were constantly bumping into each other. Think of it like this. You're at a party in a small apartment. 100 people crammed into a tiny space. You can't move without bumping into someone. Collisions happen constantly. That same party in a football stadium, same 100 people, but now they're spread across a massive area. You could walk for minutes without encountering anyone. Collision rate drops to nearly zero. That's the difference between the early universe and today. Same amount of dark matter particles, but the space has expanded enormously. The density has dropped by a factor of thousands. In the early universe, that crowded party, dark matter particles were finding each other all the time. And when they met, some of them annihilated. Each annihilation released a tiny amount of energy, but there were so many happening, so constantly, that it added up. Real heat. Significant energy pouring out of the invisible dark matter that permeated everything. A fire that needs no wood. A bonfire burning without consuming any visible fuel. Energy coming from nowhere you can see. That's what was happening in the early universe. The darkness itself was generating heat, and this changed everything about how stars could form. In today's universe, stars form one way. A cloud of hydrogen collapses under gravity. The center heats up from compression. When it reaches 10 million degrees, fusion ignites. Hydrogen burns into helium, the star shines. That's the only way it works now. But in the early universe, With dark matter so dense, there was another option, an option that created monsters. Here's what happened. A cloud of hydrogen starts collapsing, just like it would today. Gravity pulls it together, but as the cloud collapses, it's also pulling in dark matter. The dark matter is everywhere, woven through the hydrogen, like invisible threads through fabric. More and more dark matter gets concentrated in the collapsing cloud, and it starts annihilating. Particles finding each other in the compressed space, destroying each other, releasing energy. That energy heats the gas, creates pressure, pushes outward. In a normal star, this doesn't matter. Fusion happens first, providing the pressure, but in the early universe, dark matter annihilation could provide pressure before fusion ever started. And here's the key. That pressure prevented the cloud from collapsing all the way down. The hydrogen couldn't compress to the extreme densities needed for fusion. It was held open, bloated, kept enormous by dark matter energy. The cloud swelled to incredible size and started to glow, not from fusion, from the heat of dark matter destroying itself inside. A dark star was born. This could only happen in the early universe, only when dark matter was dense enough that annihilation could provide significant heat. Only in that brief window when the universe was young and packed tight. Today, impossible. Dark matter is too spread out. You'd never get enough annihilation to power a star. You'd just get normal star formation. Collapse, fusion, done. Dark stars required a universe that no longer exists. They were children of conditions that have vanished forever. It's like how giant dragonflies existed on Earth 300 million years ago. Dragonflies with wingspans over 2 feet, massive compared to modern insects. They could exist because Earth's atmosphere back then had 35% oxygen compared to 21% today. That high oxygen allowed insects to grow much larger. Their respiratory system, which relies on passive diffusion of oxygen, could support bigger bodies. Could those giant dragonflies survive in today's atmosphere? No, they'd suffocate. Their biology only works in high oxygen conditions. The environment has changed permanently. Dark stars are the same. They could only exist when the universe's dark matter atmosphere was thick enough. That atmosphere has thinned permanently. It will never return. The universe will keep expanding forever, and dark matter will keep spreading thinner. No new dark stars will ever form. The last one died over 13 billion years ago. That door has closed forever. But for a brief time, in that strange early universe, they existed, and they were spectacular. Let me show you how to build a dark star. Step by step, the birth of a monster. We're in the early universe, 300 million years after the Big Bang. Space is thick with dark matter. Hydrogen clouds float in the darkness, left over from the Big Bang. These clouds are enormous, light years across, containing enough matter to make thousands of stars. Gravity is at work, always pulling, always trying to bring things together. One cloud starts to collapse. Slowly at first, just a gentle drift inward. Over thousands of years, the cloud contracts. It fragments into smaller clumps. Each clump continues falling inward under its own gravity. This is normal star formation. This is how it starts. But something different happens here. As the cloud collapses, it's pulling in more than just hydrogen. Remember, dark matter is everywhere, and it's concentrated here in the early universe. As the hydrogen falls inward, dark matter falls inward too, invisible particles streaming into the collapsing cloud. The cloud gets smaller, denser. The dark matter gets concentrated along with everything else. And the dark matter particles start finding each other. 2 particles meet. They annihilate. A flash of gamma rays. The gamma rays slam into nearby hydrogen atoms, transferring energy. The hydrogen heats up. This happens again and again, thousands of times, millions of times. Every second, countless dark matter particles are destroying each other throughout the cloud. Each annihilation is tiny, but they add up. Real heat starts building. In a normal star formation, The cloud would keep collapsing until the center reached 10 million degrees and fusion ignited. That's supposed to be the only way to heat a stellar core. But here, dark matter annihilation is heating the core before fusion can start. The temperature rises, but not from compression alone, from invisible particles destroying themselves. The heat creates pressure. Gas pressure pushing outward. This pressure fights against gravity's inward pull. And here's the crucial part. The dark matter annihilation provides enough pressure to halt the collapse before fusion conditions are reached. The cloud can't compress down to fusion density. It's held open by dark matter energy, like trying to squeeze a balloon that keeps inflating from within. So the cloud stays large, enormously large. But it's hot. The dark matter annihilation is pumping heat into it constantly. And hot things glow. The cloud begins to shine. Not from fusion, from dark matter fuel. A dark star is born. How big can it get? In the early calculations, Catherine Fries and her team found that dark stars could grow to about 10 million times the mass of our Sunday. More recent models suggest they could get even larger under the right conditions, maybe up to 100 million solar masses. Let me give you a sense of that scale. Our Sun has a mass of about 2 times 10 to the power of 30 kilograms. That's a 2 followed by 30 zeros. Already an incomprehensibly large number. A dark star could be 10 million times that. That's 2 times 10 to the power of 37 kilograms. Here's another way to think about it. Our Sun contains 99.8% of all the mass in our solar system. All the planets, all the asteroids, all the comets combined make up only 0.2%. The Sun dominates. A dark star could contain 10 million solar systems worth of mass. 10 million suns and all their planets, all packed into one object. The size is equally staggering. Our Sun is about 1.4 million kilometers in diameter, big enough to fit over 100 Earths across its face. A dark star could be billions of kilometers across, maybe larger than the orbit of Jupiter around our Sunday, maybe larger than Neptune's orbit. Some theoretical models suggest the largest dark stars could be bigger than our entire solar system. You could be orbiting inside the star, flying through its outer atmosphere. The star wouldn't be a bright disk in your sky. The star would be your sky. Glowing gas in every direction, stretching to the horizon and beyond. What would it look like up close? You approach one of these giants. From far away, it looks like a bright, fuzzy sphere. As you get closer, you realize there's no sharp edge, no clear boundary where star ends and space begins. It's more like flying into a glowing mist that gradually gets brighter and denser. You pass into the outer layers. Around you, thin hydrogen gas glowing with a reddish light. The temperature here is maybe 20 or 30,000 degrees Celsius, hot enough to vaporize any solid matter instantly. But for a star, relatively cool. The Sun's surface is about 6,000 degrees. Its core is 15 million. You go deeper, the gas gets denser, the glow intensifies. You're inside the star now, though it doesn't feel like you'd expect. There's no crushing pressure, no blinding light from a central point, just brightening fog in all directions. And all around you, invisible to your eyes, dark matter particles are meeting and destroying each other. Trillions of tiny annihilations every second, each one releasing a burst of gamma rays. The gamma rays scatter through the gas, their energy absorbed and re-emitted as visible light and heat. You're witnessing something impossible. A star powered not by nuclear fusion, but by the annihilation of matter you cannot see. The invisible skeleton of the universe, catching fire and glowing. The core of a dark star never gets hot enough for fusion. That's the key difference. A normal star's core reaches 15 million degrees because of extreme compression. Fusion ignites. Hydrogen burns to helium. A dark star's core might only reach a few million degrees. Hot, but not hot enough for fusion. The star is held up by dark matter pressure, not fusion pressure. It doesn't need fusion. It has a different power source. How bright are these things? A single large dark star could outshine 10 million suns. That's as bright as a small galaxy. All that light coming from one object. To put that in perspective, our Milky Way galaxy contains about 200 billion stars. Most of them are dimmer than the Sunday. If you added up all their light, the Milky Way shines with the luminosity of about 20 billion suns. A single dark star is nowhere near that bright, but it's bright enough that from a great distance, it could be mistaken for a small galaxy, which is exactly what happened with JWST. Astronomers saw these bright spots and thought galaxies, collections of millions of stars, when in reality, each spot might be a single dark star, one massive, strange, impossible object. How long can a dark star shine? That depends on how much dark matter is available and how fast it's being consumed by annihilation. Early calculations suggested dark stars could exist for about 1 million years, maybe up to 10 million years in ideal conditions. That sounds like a long time, but for stars, it's nothing. Our sun will live for about 10 billion years total. It's already 4.5 billion years old, middle-aged. Most normal stars live for millions or billions of years. A dark star's lifespan is measured in millions of years at most. They're brief candles, burning bright but not for long, and they can only exist in the early universe. Only when dark matter is concentrated enough. As the universe expands, as dark matter spreads thinner, the fuel runs out. Not because dark matter disappears. It's still there, but it's too dispersed. The collision rate drops. Annihilation becomes rare. The energy output decreases. The star begins to fail. Over time, maybe hundreds of thousands of years, the dark matter density drops below the critical threshold. The annihilation energy isn't enough anymore to hold the star up against gravity. Gravity wins. The star begins to collapse. And now, finally, fusion has its chance. As the star collapses, the core heats up from compression. The temperature rises, 10 million degrees. Fusion ignites. Hydrogen starts burning the normal way. The dark star transforms. It becomes a regular star. Well, regular in the sense that it's now powered by fusion, but it's still enormous. A supermassive star, far larger than anything that forms today, and massive stars burn fast and die young. Where our sun will burn steadily for 10 billion years, a supermassive star might last only a few million years. It races through its hydrogen fuel, burns helium, then carbon, oxygen, heavier and heavier elements. Finally, the core runs out of fuel. Fusion stops. Nothing left to burn. Gravity crushes the core. The star explodes in a supernova, one of the first explosions in the universe. The blast wave races outward at a significant fraction of light speed. The star's outer layers, containing all the heavy elements forged in its core and in the explosion itself, scatter through space. Carbon, nitrogen, oxygen, iron, the building blocks of planets, of life. And the core? If the star was massive enough, the core collapses into a black hole, not a stellar mass black hole of a few dozen suns. A massive black hole, hundreds or thousands of solar masses. These might be the seeds of the supermassive black holes we find at the centers of galaxies today. Black holes containing millions or billions of solar masses. We don't fully understand how they got so big. Dark stars provide one possible explanation. Start with a massive black hole seed from a dark star's death, then let it grow over billions of years. But the dark star itself? Gone. That strange phase, powered by invisible annihilation, existed for only a brief time, 1 million years, maybe 10 million. Then it transformed into something else and eventually died. And no new dark stars will ever be born. The conditions are gone. Dark matter is too thin. The universe has changed in a way that makes them impossible. For a brief cosmic moment, the invisible skeleton of the universe caught fire and glowed. Then that moment ended, forever. Why dark stars had to die, why they couldn't last, why the universe itself killed them. The answer is expansion. The universe has been expanding since the Big Bang, not expanding into anything, Space itself is stretching. Every point in space is getting farther from every other point. A balloon with dots marked on its surface. As you inflate the balloon, the dots move apart. None of the dots is the center of the expansion. Every dot sees all the other dots moving away from it. That's what's happening with space. Edwin Hubble discovered this in 1929. He measured the light from distant galaxies and found that they were all redshifted. Their light was stretched to longer, redder wavelengths. The farther away a galaxy was, the more redshifted it appeared. This redshift is caused by the expansion of space. As light travels through expanding space, it gets stretched along with the space, and the amount of stretching depends on how long the light has been traveling. Light from very distant galaxies has been traveling for billions of years, so it's been stretched a lot. Hubble's observation led to a profound realization. If the universe is expanding now, it must have been smaller in the past. Wind the clock back far enough, and everything was compressed into an infinitesimally small point, the Big Bang. Since the Big Bang, the universe has been expanding. In the early moments, it expanded incredibly fast. Then the expansion rate decreased but never stopped. The universe today is still growing larger, and as it grows, everything in it gets more diluted. Think about it this way. Take a cubic meter of space today. Count how many dark matter particles are in that volume. Now go back to the early universe, 300 million years after the Big Bang. Take the same cubic meter. It contains far more dark matter particles because the universe was smaller and everything was packed closer together. As the universe expanded, that cubic meter stretched. The particles that were once close together spread farther apart. The density decreased. Today, dark matter has an average density of about 0.3 protons per cubic meter in intergalactic space. That's incredibly thin. For comparison, the best vacuum we can create on Earth still contains millions of particles per cubic meter. In the early universe, dark matter density was thousands of times higher. Not because there was more dark matter, same amount, just compressed into a smaller space. And this matters for dark stars because their power source depends on density. Dark matter annihilation only produces significant energy when particles are close enough together to collide frequently. In the dense early universe, collisions happened all the time. In the thin modern universe, collisions are vanishingly rare. A dark star requires a constant stream of annihilation energy to stay inflated. When the density drops below a certain threshold, the annihilation rate falls. The energy output decreases. The star can't maintain itself. You're trying to keep a hot air balloon inflated by lighting matches underneath it. As long as you can light enough matches fast enough, the balloon stays up, but if your match supply starts running low, you can't generate enough heat. The balloon begins to sink. Dark stars face the same problem. As the universe expanded around them, as dark matter density decreased, their fuel supply dwindled. If the entire 13.8 billion year history of the universe was compressed into one calendar year, starting January 1st and ending December 31st, when did dark stars exist? The Big Bang happens at midnight on January 1st. The first dark stars might have formed around January 2nd or 3rd, once the universe had cooled enough for matter to clump together but was still dense with dark matter. By January 4th or 5th, dark matter had spread too thin. Dark stars couldn't form anymore. The ones that already existed started to fail. By the end of the first week of January, they were all gone. We're living in late December now. It's December 31st, about 11 at night. Humans appeared in the last 10 seconds before midnight. Recorded history is the last fraction of a second. Dark stars existed only during the first few days of the cosmic year. They've been gone for 51 weeks. Essentially, the entire year has passed since the last one died. Some things can only exist once. Some doors close permanently. Dark stars are one of those things. The universe today cannot make them. Even if you somehow gathered enough hydrogen in one place, even if you perfectly recreated the conditions of star formation, you wouldn't get a dark star. You'd get a normal star, because dark matter isn't dense enough anymore to provide the annihilation energy. It's like trying to recreate those giant dragonflies I mentioned earlier. You can't, not in today's atmosphere. Even if you had their DNA, even if you could clone one, it would suffocate. The oxygen levels are wrong. The environment has changed in a fundamental way. The universe has changed the same way. Dark matter density is too low. That condition is permanent. The universe will keep expanding forever, and dark matter will keep spreading thinner. No new dark stars. Ever. That chapter of cosmic history has closed. What happened to the individual dark stars that did exist? They burned for maybe 1,000,000 years, some perhaps longer, up to 10 million years if they were especially massive or existed in particularly dense regions. Then the annihilation rate dropped below the critical threshold. The dark matter energy couldn't hold them up anymore. Gravity began to win. The star collapsed. As it collapsed, the core heated up from compression. The temperature climbed. 5 million degrees, 8 million, 10 million. Fusion ignited. Suddenly, the star had a new power source. Not dark matter annihilation, but nuclear fusion. Hydrogen burning into helium, releasing energy through mass conversion. The collapse halted. The star reached a new equilibrium. But this new star was still enormous, far more massive than any star that forms in today's universe. A supermassive star, perhaps 1,000 or 10,000 times the mass of our Sun. And massive stars have short lives. The more massive a star, the faster it burns its fuel. Our Sun will live about 10 billion years. A star 10 times more massive might live only 10 million years. A star 100 times more massive might last only a few 100,000 years. These transformed dark stars, now burning fusion, raced through their fuel. They burned hydrogen, then helium, then carbon, neon, oxygen, silicon, building up heavier and heavier elements in their cores through fusion. Finally, they reached iron. Iron is the end of the line for fusion. Fusing iron doesn't release energy. It consumes energy. Once a star's core turns to iron, fusion stops. No more energy generation. No more pressure to hold up the star. The core collapses in a fraction of a second. The temperature and density spike to incredible levels. The outer layers of the star, suddenly unsupported, fall inward, then bounce off the collapsing core and explode outward. Supernova. The explosion is so energetic that it briefly outshines an entire galaxy. For a few weeks, this one exploding star is as bright as billions of normal stars combined. And the explosion does something crucial. It scatters all the heavy elements that were built up in the star's core through space. Carbon, nitrogen, oxygen, all the elements up to iron and beyond. Elements that didn't exist before stars made them. The Big Bang only created hydrogen, helium, and a tiny bit of lithium. Everything else had to be made in stars. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it forged in stellar cores and scattered by supernovas. Dark stars, when they died, were among the first to perform this alchemy. Among the first to create and scatter heavy elements. They seeded the early universe with the building blocks of planets and life. Their deaths also triggered new waves of star formation. When a supernova blast wave passes through a gas cloud, it compresses the gas. That compression can trigger the cloud to collapse and form new stars. One dying star giving birth to many new ones. And the cause of these dying dark stars? They collapsed into black holes. Not small stellar mass black holes, massive ones. Hundreds or thousands of solar masses. These might have been the seeds that grew into the supermassive black holes we find at the centers of galaxies today. Black holes containing millions or billions of solar masses. We observe these giants in almost every large galaxy, including our Milky Way, but we don't fully understand how they got so big. Dark stars provide one possible explanation. Start with a large seed, a black hole of hundreds or thousands of solar masses from a dark star's death. Then let it grow over billions of years, accreting more matter, merging with other black holes. Eventually, you get the monsters we observe today. But dark stars themselves? Gone. Extinct. That brief phase of their existence, powered by dark matter, lasted maybe 1 million years. Then they transformed into fusion-powered stars and burned out in a few more million years. Total lifespan from birth to death? Perhaps 10 million years at most, possibly much less. And they existed only in a brief window of cosmic history, the first few 100 million years after the Big Bang. Then the universe aged past them, left them behind. We are living in a universe that has completely moved on from the dark star era. They are as distant from us in time as we could possibly be from anything. Creatures from the universe's strange childhood, we're seeing cosmic fossils, evidence of life forms that went extinct 13 billion years ago and can never evolve again because the environment that created them no longer exists. Some doors close forever. The universe can never make another dark star. That possibility is gone, permanently. And there's something profound about that, something worth sitting with. But dark stars didn't just exist and disappear. They left something behind, a legacy that shaped everything that came after, including you. Let me tell you what they did. They lit the first dawn. The universe, 400 million years after the Big Bang, before dark stars. It's dark, truly dark. The Big Bang's afterglow has faded to a dull background hum. Matter has cooled into hydrogen and helium gas. Clouds float through space, but there are no stars yet. Or if there are, they're rare and dim. This period is called the Cosmic Dark Ages, a time when the universe had cooled from its brilliant beginning but hadn't yet lit up with starlight, darkness and fog, neutral hydrogen gas filling space, opaque to light. Then dark stars ignite, these massive, brilliant objects scattered through the early universe, each one shining with the light of millions of suns. Suddenly, there's real light, substantial illumination. The darkness begins to recede, and that light does something crucial. It ionizes hydrogen. Hydrogen in its normal state is neutral. One proton, one electron, bound together. Neutral hydrogen absorbs light. It's opaque. If space is filled with neutral hydrogen, it's foggy. Light can't travel far before being absorbed. But high-energy ultraviolet light can strip electrons away from hydrogen atoms. This is called ionization. Ionized hydrogen is just naked protons, and ionized hydrogen is transparent. Light can pass through it freely. Dark stars pumped out enormous amounts of ultraviolet light. This light slammed into the surrounding hydrogen gas, ionizing it. Each dark star created a bubble of transparent space around itself, clear zones in the cosmic fog. As more dark stars formed, the bubbles grew and merged. Gradually, the universe transitioned from foggy and opaque to clear and transparent. This is called reionization, one of the major phase transitions in cosmic history. We know reionization happened because we can see distant galaxies clearly. If space was still full of neutral hydrogen, we couldn't see them. Dark stars might have started this process, or at the very least, contributed significantly to it. They were among the first sources of light powerful enough to ionize hydrogen on a large scale. They cleared the cosmic fog, made space see-through, created the conditions where light could travel freely and we could eventually observe the universe. Without reionization, the universe would be perpetually foggy, opaque. Light from distant objects would be absorbed after traveling only short distances. We couldn't see galaxies, couldn't study the cosmos. The universe would be fundamentally different. Dark stars helped make the universe transparent. They lit the way, but that's not all they did. When dark stars died, they scattered heavy elements. I mentioned this earlier, but let me emphasize how important this is. The Big Bang created hydrogen and helium. That's it. Trace amounts of lithium, but nothing heavier. No carbon, no oxygen, no nitrogen, silicon, iron, none of the elements that make up planets and life. Those elements had to be created in stars. Fusion in stellar cores builds heavier elements from lighter ones. Hydrogen fuses to helium. Helium fuses to carbon. Carbon to oxygen. And so on, up through the periodic table. But these elements stay locked inside the star unless something violent happens to scatter them. That's where supernovas come in. When a massive star explodes, it throws its guts into space. All those heavy elements built up over the star's lifetime get scattered through the interstellar medium. Future generations of stars form from gas clouds enriched with these elements. Planets form from the heavy elements. Life, at least life as we know it, requires carbon, nitrogen, oxygen, phosphorus, all made in stars. Dark stars were among the first to die as supernovas, among the first to scatter heavy elements. They seeded the early universe with the building blocks of everything complex. The carbon in your DNA, made in a star, possibly in a dark star billions of years ago. The oxygen you're breathing right now, forged in a stellar core. The calcium in your bones, the iron in your blood, the phosphorus in your cell membranes, all star stuff. Some of those atoms might have cycled through a dark star, might have been present in its core, might have been ejected in its supernova and scattered through space for billions of years before eventually ending up in you. You are connected to the universe's first stars through chains of atoms that stretch across cosmic time. Dark stars also triggered more star formation. When a supernova explodes, the blast wave races outward at thousands of kilometers per second. When that shock wave slams into a nearby gas cloud, it compresses the gas, squeezes it, makes it denser, and denser gas is more likely to collapse under its own gravity and form stars. So one dying dark star might trigger the formation of hundreds or thousands of normal stars in its vicinity. One death seeding many births. This created a cascade. Dark stars formed, lived briefly, died, and their deaths triggered new star formation. Those new stars eventually died and triggered even more star formation. Generations of stars, each one building on what came before. Without that initial push, without those first massive stars living and dying and scattering their material, the universe's evolution would have been slower, possibly much slower. The complex chemistry needed for planets and life might have taken much longer to develop. Dark stars accelerated cosmic evolution. They jump-started the process of building complexity. And then there are the black holes. When dark stars collapsed and exploded, their cores formed black holes. Massive black holes, far larger than what you get from normal stellar death. A normal star, even a massive one, leaves behind a black hole of maybe 10 or 20 solar masses. That's the typical range for stellar mass black holes. But dark stars could leave behind black holes of hundreds or thousands of solar masses, maybe more in extreme cases. These are big enough to serve as seeds for supermassive black holes. The giants we observe at the centers of galaxies, containing millions or billions of solar masses. We know these supermassive black holes exist. We've observed them directly now, even photographed the glowing gas swirling around them. The Event Horizon Telescope captured an image of the supermassive black hole at the center of the galaxy M87 in 2019, 65 billion solar masses. A monster? Our own Milky Way has a supermassive black hole at its center called Sagittarius A star. About 4 million solar masses. We've watched stars orbit around it, tracing out elliptical paths under its immense gravity. But we don't fully understand how these giants formed. How do you grow a black hole from a few solar masses to millions or billions? You can accrete matter onto it, black holes pulling gas and dust and stars that wander too close. But that process is slow. Calculations suggest it's hard to grow a black hole to supermassive size in the time available, unless you start with a bigger seed. If dark stars left behind black holes of thousands of solar masses, that gives you a head start. Now you only need to grow from thousands to millions, not from tens to millions. That's much more plausible in the time available. Dark stars might have seeded the universe with the first generation of massive black holes. Those black holes then grew over billions of years into the supermassive ones we observe today. We don't know this for certain. It's one hypothesis among several, but it's a compelling one. Dark stars solve multiple problems at once. They explain the early bright objects JWST observed. They provide a mechanism for seeding supermassive black holes. They help explain reionization, one idea that ties together several mysteries. But here's what gets me. Here's what keeps me up at night thinking about this. None of this was intentional. Dark stars didn't choose to light the universe or seed it with heavy elements. They were just objects following the laws of physics. Born in certain conditions, living according to the rules of thermodynamics and gravity, dying when their fuel ran out. They had no purpose, no goal. They just existed, and yet their existence changed everything, made possible everything that came after. The stars you see in the night sky? They might not exist if dark stars hadn't cleared the cosmic fog and triggered the first waves of star formation. The planets orbiting those stars? They couldn't form without the heavy elements dark stars scattered. Life? Life as we know it requires complex chemistry, carbon-based molecules, water, minerals. None of that is possible without heavy elements, without stars that lived and died and created those elements. You exist because dark stars existed first, because they lit the dawn, because they died and scattered their material, because they created the conditions for stars like the sun to form, for planets like Earth, for life to emerge. There's a chain of causation stretching from those first giants to you, billions of years, countless intermediate steps, but an unbroken chain nonetheless. The universe had to be strange once, so it could be stable now. It had to birth monsters, so it could eventually birth you. Think about that. Those impossible stars, burning darkness, shining for a brief time in the early universe, and then dying. They made you possible, and they never knew. They couldn't know. They were just balls of gas and dark matter, following physics. But without them, you're not here. That's the legacy of dark stars. Not intentional, not planned, just the consequence of existing at the right time, in the right conditions, and following the laws of nature. They transformed the universe by simply being what they were, and then they stepped aside, vanished, made room for what came next. There's something beautiful about that, something profound, things that create the conditions for what comes after, then disappear so the new thing has space to flourish. Let me bring this home to you now. Make it personal. You're here, right now, wherever you are, maybe lying in bed, maybe sitting quietly, maybe walking. You exist. You're aware. You're experiencing this moment. That simple fact required an extraordinary chain of events. It required the Big Bang 13.8 billion years ago, the origin of space and time and energy. It required the universe to expand and cool enough for atoms to form. Hydrogen and helium condensing out of the primordial plasma. It required tiny quantum fluctuations in the early universe to grow into cosmic structure. Little ripples of density that gravity amplified over billions of years into galaxies and clusters and the vast web we see today. It required dark matter to clump together, creating gravitational wells where normal matter could gather. It required the first stars to form, and not just any stars. It required dark stars, giants that could light the universe and scatter heavy elements and trigger cascades of star formation. It required those dark stars to die so their atoms could be recycled into new stars. It required generation after generation of stars, living, dying, creating heavier elements, scattering them through space. It required our particular galaxy, the Milky Way, to form about 13 billion years ago. A spiral galaxy with hundreds of billions of stars, rotating slowly in space. It required a particular region of that galaxy, about 26,000 light-years from the center, to have the right density and composition. It required a cloud of gas and dust to collapse about 4.6 billion years ago, forming our sun and the planets. Getting the distances right. Earth in the habitable zone, where water can be liquid. It required Earth to be the right size to hold an atmosphere, the right composition to have a magnetic field that protects against radiation, the right orbit to maintain stable temperatures. It required billions of years of geological evolution, the formation of oceans, the development of plate tectonics, the carbon cycle, the atmosphere gradually enriching with oxygen from photosynthetic life. It required life to emerge, somehow, from non-living chemistry. We still don't fully understand this step, but it happened. About 4 billion years ago, single cells in the ancient ocean. It required billions of years of biological evolution, from simple cells to complex cells with nuclei, from single cells to multicellular organisms, from ocean to land, from fish to amphibians to reptiles to mammals, from small mammals to primates, from primates to humans. It required your specific ancestors to survive. Every single one. An unbroken chain of survival stretching back billions of years. Not one of your ancestors died before reproducing. Not one. It required your parents to meet, your grandparents to meet. Every coupling in your family tree, going back thousands of generations, had to happen exactly as it did. And finally, it required you to be the particular sperm and egg that combined. One specific sperm out of millions. One specific egg out of thousands. Every link in that enormous chain had to hold. One break anywhere and you're not here. And early in that chain, crucial to it, were dark stars. Those giants that shone in the early universe. That burned matter we can't see. That existed for a cosmic eye blink and then vanished forever. Without them, or without something performing their function, the universe's evolution would have been different. Slower, perhaps. Structured differently. Maybe unable to produce the conditions that eventually led to you. You are 13.8 billion years of cosmic evolution. You are the universe's way of becoming aware of itself, of looking back at its own history and wondering, and part of that history, part of that long story, includes stars that can never form again. The atoms in your body are ancient. The hydrogen atoms in your water molecules, in your organic compounds, those are truly ancient. They formed in the first few minutes after the Big Bang, when the universe was hot and dense and undergoing nuclear reactions. Those hydrogen nuclei, those single protons, are 13.8 billion years old. They've been around since the beginning, cycling through clouds and stars and planets, spending time in the ocean, in the atmosphere, in countless organisms before you. Those atoms are older than Earth, older than the Sun, almost as old as the universe itself. But the heavier atoms? The carbon, nitrogen, oxygen, phosphorus, sulfur, the calcium in your bones, the iron in your blood, those were made in stars. Fusion in stellar cores built those atoms from lighter elements. Then supernovas scattered them through space. They drifted in interstellar clouds for millions or billions of years. Eventually, they were incorporated into the cloud that formed our solar system. They became part of Earth, part of you. Some of those atoms might have passed through a dark star, might have been part of that giant's atmosphere or core, might have been present when the star died in a supernova 13 billion years ago. Those atoms scattered through space, mixed with other material, became part of new gas clouds. New stars formed from those clouds, lived and died. The atoms cycled through generations of stars, being forged into heavier elements, scattered again, collected again. Eventually, they ended up in the cloud that formed our solar system, condensed into Earth, became part of the ocean, the rocks, the atmosphere, were taken up by living organisms, passed through the food chain, eventually incorporated into you. You carry fragments of the universe's first stars inside you. Atoms that have cycled through the cosmos for over 13 billion years before becoming part of you. You are made of star stuff, including stuff from stars that can never burn again. There's a direct physical connection between you and those impossible giants. Not just a metaphorical connection, an actual material link. The same atoms that once floated in a dark star's glowing atmosphere might now be part of your body. You are carrying the universe's strange childhood within you. Look up at the night sky tonight if you can. If you're somewhere dark enough to see stars, those familiar points of light, they're normal stars. Stars like the Sunday burning fusion in their cores, hydrogen to helium, stable, long-lived, following the rules you understand. They're only there because giants came first. Every star you see exists in a universe that dark stars helped shape. A universe that dark stars lit and cleared and seeded with heavy elements. A universe that dark stars transformed before dying. Those normal stars are beneficiaries of what dark stars did, children of the conditions dark stars created, living in a universe made possible by dark stars' brief, strange existence. You're looking at the legacy of monsters. Giants powered by invisible fire. Giants that existed in conditions so alien we can barely model them. And somewhere out there, 13.5 billion light years away, the light from those dark stars is still traveling. Light moves at a finite speed, 300,000 kilometers per second, fast by human standards, but slow on cosmic scales. Light from the sun takes 8 minutes to reach Earth. Light from the nearest star takes over 4 years. Light from the early universe has been traveling for over 13 billion years, still moving through space, still carrying information about the conditions back then. JWST caught some of that light. Photons that left a dark star when the universe was 300 million years old. They've been traveling ever since, through expanding space, getting redder as the space stretched, finally arriving at JWST's mirror, where they were focused onto detectors and converted into the data we analyzed. We caught a glimpse of those ancient giants, a photograph from the universe's childhood, evidence of a time when the rules were different, when stars could burn darkness. We'll never see dark stars directly. We'll never visit one. We can't recreate them. The universe has moved on. The conditions that allowed them are gone forever, but we can study them through their light. Ancient light that's been traveling since before our solar system existed, before Earth formed, before life began. A universe so different from ours that the fundamental processes worked on completely different principles, and we can understand our place in that story. We are late arrivals, living in a universe that dark stars helped build, existing because they existed first, shone brightly, scattered their material, and died. The universe had to be strange once so it could be stable now. It had to birth monsters so it could eventually birth you. Think about the universe's capacity for strangeness, for creating things that seem impossible, things that break our intuitions about how reality should work. Stars that burn invisible matter. Black holes where space curves so severely that nothing can escape. Quantum particles that exist in multiple states simultaneously until observed. The expansion of space itself, accelerating under the push of dark energy. And that weirdness was necessary. If the early universe had been safe and normal and predictable, if it had only made small, sensible stars, the cosmos might never have evolved the complexity we see today. Sometimes you need the impossible to make the possible possible. Sometimes you need monsters to clear the way. Dark stars were impossible, giants that defied normal stellar physics, stars that shouldn't work, powered by matter we can't see, existing only when the universe was young and dense and strange. And because they were impossible then, you're possible now. That's the cosmic trade. The bargain written into the fabric of reality. The universe's strange childhood for its stable adulthood. The age of dark stars for the age of planets and life and complexity. Some things can only exist once. Some doors close and never reopen. Dark matter will never be dense enough again. The universe will keep expanding forever, getting larger, colder, more diffuse. The expansion is even accelerating, pushed by dark energy. In the far future, billions of years from now, the universe will be even more spread out than today. The conditions that allowed dark stars will never return. They can't. The physics doesn't allow it. The universe's expansion is one way. You can't compress space back down. You can't reverse cosmic time. No new dark stars will ever form. The last one died over 13 billion years ago. Transformed into a normal supermassive star, burned out in a few million years. Exploded as a supernova. Their time is done. That chapter of cosmic history has closed permanently. And there's something profound about that. Something worth contemplating as you drift towards sleep. The universe had a moment of strangeness, a brief window when impossible things existed, Then that window closed. The universe settled into stability, into the patterns we observe today. And that transition, that transformation from strange to stable, made everything you see around you possible. Dark stars were the universe's way of lighting its path forward, of bootstrapping itself from simple to complex, from dark to bright, from empty to full. They existed, they shone with light from invisible annihilation. They died and scattered their atoms, and their gift was everything that came after, including you. Every breath you take involves atoms that might have cycled through a dark star. Every heartbeat pumps blood with iron that might have been forged in one of those giants. You are connected to the universe's strangest era, linked to it by chains of atoms and causation stretching across billions of years. And that connection runs both ways. Those dark stars, if they could have known, if stars could think, were creating the future, creating conditions for things they'd never see, things that could only exist after they were gone. They burned darkness to light the way for something that hadn't been imagined yet, something that required their death to be born. There's something beautiful about that, something poetic. Things that create the conditions for what comes next, then step aside, disappear so the new thing has room to exist. Dark stars lit the universe's first morning. They burned away the fog. They seeded space with heavy elements. They triggered cascades of star formation. They created the first massive black holes. Then they vanished, made room for normal stars, stars that could burn steadily for billions of years, stars that could have planets, stars that could nurture life. They created a universe they couldn't survive in, and in doing so, they made you possible. So tonight, as you drift towards sleep, hold this thought. The stars you see, those familiar points of light, are children of giants you'll never see. Giants that burn the invisible, giants that existed once and can never exist again. And you are made of those giants. Literally, your atoms cycled through them. Your existence depends on what they did. You are star stuff, including stuff from stars that can never burn again. The cosmos had one brief moment of strangeness, one window when dark matter was dense enough, when the universe was young enough, when physics allowed something impossible. Dark stars burned in that window, shone brilliantly. Then the window closed behind them, and they left us this universe, this stable, well-lit, element-rich universe where complexity can flourish, where planets form, where life emerges, where conscious beings can look up at the stars and wonder. Their legacy is everything. Rest easy tonight knowing you're part of that story, part of the impossible made possible, part of 13.8 billion years of cosmic evolution. You exist because the universe was once strange enough to create monsters, and those monsters were generous enough to die. Sleep well, knowing the universe once broke all its rules just to make this moment possible, just to create the long chain of events that led to you, here, now, aware and alive and wondering. The light from dark stars is still out there, still traveling through expanding space, carrying the story of the universe's strangest childhood across the cosmic ocean. We caught a glimpse of it, and it changed everything we thought we knew. The universe is stranger, more wonderful, more full of impossible beauty than we ever imagined. And you're part of that impossibility, made of atoms from stars that can never burn again, living in a universe those stars helped create. Dark stars were temporary, brief, gone now forever. But their gift remains. In the transparent universe, they helped clear. In the heavy elements, they scattered. In the black holes, they seeded. In the cascade of star formation, they triggered. In you, you are their legacy. The distant consequence of giants that burned darkness 13 billion years ago. And that's beautiful. Sleep well,